When you sit down at the controls of like a really heavy piece of physical machinery, say a forklift, or even an airplane cockpit,
Right.
there's this inherent expectation of physical logic.
Right.
If you pull the emergency eject lever, you physically cannot be, simultaneously engaging the landing gear. The actual hardware, the literal metal and hydraulics, they prevent it. You pull one lever and the other one is just mechanically locked out.
Because the machine is binary by design. I mean, the engineers who built it made absolutely sure that executing two completely contradictory actions at the exact same millisecond is, well, it's physically impossible.
Right. You don't even have to trust the pilot to remember it.
Exactly. The cockpit simply won't let them make that mistake.
But then you step into the world of software engineering, and suddenly that physical logic just completely vanishes.
Yeah, it's gone.
You're looking at this digital control panel where you can, metaphorically speaking anyway, deploy the parachute, fire the rocket thrusters, and just dump all the fuel tanks at the exact same moment.
Right.
We give ourselves so much flexibility in our code that we actually build systems that allow us to break them. We create these environments where contradictory states aren't just possible, they are like passively encouraged by the tools we use.
Which is pretty much the absolute definition of a structural trap.
Yeah.
And it's a trap we fall into constantly, because we tend to confuse flexibility with power. We sort of think that having zero constraints makes us better problem solvers.
Well, we can do anything.
Exactly. When in reality, it just forces us to spend half our time anticipating exactly how the system might just tear itself apart.
So welcome to today's deep dive.
Yeah.
We are exploring a really powerful programming philosophy today that, frankly, completely changes how we think about errors, mistakes, and just system design from the ground up.
It's a total paradigm shift.
It really is. And we're focusing on a single, absolutely fascinating source for you today. It's a blog post that just dropped today, actually, August 6th, 2026.
Fresh off the press.
Yep, it's titled Notes-on-Haskell-Programming, Part 206, Making Illegal States Unrepresentable. And it's written by a developer named Ang.
Which is a great title, by the way.
It's so good. And the core mission for you today is to understand this brilliantly counterintuitive mental model, making it structurally impossible to make a mistake rather than, endlessly trying to catch those mistakes after they happen.
And I want to point out, even if your day-to-day work doesn't involve writing hardcore functional programming code, this concept is incredibly potent.
Oh, totally.
It applies to solving complex problems in management, in product design, and just how we architect our daily workflows. Because what Ang is really talking about here is environment design.
Right.
It's about recognizing that human error is usually just a symptom of a poorly designed system.
Okay, let's unpack this. Because to really appreciate the brilliance of Ang's solution here, we first have to sort of wade into the mess. We have to experience the problem Ang actually describes in the post.
We have to feel the pain first.
Exactly. So Ang uses this very familiar scenario, handling data fetched from an API for a user interface. Now, we all know the three basic phases a UI goes through during a fetch. First, it's loading.
Right.
Second, it's loaded with the data. Or third, it completely failed and you have an error on screen.
Just three distinct sequential phases. Simple enough.
Simple, right. But Ang points out that the way programmers traditionally represent these states behind the scenes is, well, fundamentally flawed.
Yeah, the trap really lies in how those three phases are mapped into the memory of the application. The standard approach, this is the one taught in almost every introductory web development course out there, is to track the status of that API call using three independent Boolean variables.
Okay, lay that out for us.
So you basically set up your state object with iLoading set to false, has error set to false, and user data set to null.
Which, I have to admit, seems entirely logical at first glance.
It does.
You have a switch for your loading state, you have a switch for your error state, and a bucket to basically hold the data when it arrives. It feels very organized.
It feels like you've covered all your bases.
Right. But let's bring this back into the physical world for a second to see the flaw. Let's say you're tasked with designing a traffic light. The safe, logical way to design it is to ensure only one light, red, yellow, or green, can physically be illuminated at a time.
Naturally.
But this programming approach, using those three independent variables, it's like installing three completely separate independent wall switches in a control room for that one traffic light.
Oh, that's a great way to put it.
One switch for red, one switch for yellow, one switch for green. And if they are completely independent switches on a wall, what is physically stopping a rogue operator or, just a chaotic network delay from flipping them all on at once?
Well, nothing at all. You have completely decoupled the constraints. And when you decouple constraints in software, you are just opening the door to mathematics. Since each of those three independent variables can be in one of two states, true or false, or, empty and full for the data, you multiply the possibility.
2 times 2 times 2.
Exactly. By trying to manage just three simple phases, you have inadvertently engineered 8 possible combinations of state right into your system.
8 states.
Yeah.
For a process that only has 3 actual phases in reality.
Yeah. Loading, loaded, or error.
That expansion is just wild when you actually stop and think about it.
It's a geometric explosion of complexity. And developers often view this through the lens of well, look, I've built a highly flexible system.
Right, they see it as a feature.
We have this ingrained bias that more state variations mean more control. But this is a massive liability.
Why is that?
Because in complex asynchronous environments, like a modern front-end application where network requests are racing each other and, users are clicking buttons wildly if your system can enter a state, eventually, under the right chaotic conditions, it will enter that state.
Murphy's Law of Code.
Pretty much.
So let's walk through the reality of those 8 combinations, because Ang is very clear in the post about this. Of those 8 possible states, 5 of them are completely, quote-unquote, illegal.
Yes. Meaning they're just logically wrong.
Right. They represent a reality that makes absolutely no sense in the real world.
They are pure contradictions.
Give me an example of a mild one.
Okay, take a relatively benign one. What if ID loading is false and has error as false, but user data is also still null?
Okay, so the application isn't loading anything.
Right.
It hasn't registered a failure.
Right.
But it has no data to show you either.
Exactly. From the user's perspective, they are staring at a completely blank screen forever.
Right.
The app is basically in purgatory. It thinks everything is fine, but nothing is actually happening.
I have definitely stared at that exact blank screen on plenty of websites.
We all have.
But Ang highlights one specific nightmare scenario in the post. State number 5.
Oh, state 5.
This is the one where iLoading is true, ND has error is true, and user data actually contains the payload.
Yeah, so going back to your traffic light analogy, that is the red, yellow, and green bulbs all blindingly illuminated at the exact same time.
Wow.
The system is simultaneously screaming, "Please wait, I'm fetching the data," while also shouting, "I failed, the data is broken," while also saying, "Here is your data, please look at it."
What actually happens to a front-end application when it hits state 5? I mean, functionally, what does the user actually see?
Well, does it just render a loading spinner directly on top of an error message, directly on top of their profile data?
Yeah, how does the browser even handle that?
It completely depends on how the UI rendering logic was written, which is exactly why it's so incredibly dangerous.
Right.
Best case scenario, it just looks terrible, like a visual glitch where elements just overlap weirdly.
And the worst case?
Worst case scenario, especially in complex applications like, say, financial dashboards or medical record systems, the application essentially tears itself apart trying to reconcile the irreconcilable.
Oh, wow.
It might trigger an infinite retry loop because the error switch is flipped, while simultaneously trying to parse the data payload, which spikes memory usage and just crashes the entire browser.
Okay, hold on, though. I look at this 3 Boolean setup, and part of me just thinks, we'll just write better code. If you know state 5 is a disaster, just be disciplined. Don't write the logic that triggers state 5. Make absolutely sure you toggle the loading switch off before you toggle the error switch on.
Right.
Why is this such an insurmountable problem that we need a whole philosophical shift to solve it?
Because you are relying on human discipline to patch over a systemic architectural flaw.
Okay.
When you rely on discipline, you are just guaranteed to fail at scale. A single developer working on a tiny script, sure, they might be able to keep those state transitions perfectly balanced in their head.
For a while, maybe.
Exactly. But add 10 more developers, an aggressive deadline, and a code base with hundreds of thousands of lines of code.
Someone's going to slip up.
Someone is absolutely going to forget to toggle a switch. And because the independent switches are sitting right there in memory just waiting to be flipped in the wrong combination, developers are forced into this deeply exhausting posture.
Defensive programming.
Yes.
Yeah.
They have to anticipate the chaos of their own architecture. They spend their time building scaffolding rather than the actual building.
Yeah, they have to write lines and lines of guardrails just to double check that the system hasn't, tied itself into a knot.
Exactly. You end up with these massive, deeply nested if statements. If it is loading, make absolutely sure the error switch is turned off. And if the error switch is turned on, run a function to manually clear out any data in the bucket just in case.
Right. Aang really refers to this in the post as writing defensive codes and relying on hackish logic to handle these impossible edge cases. It really sounds like you're writing code to babysit your own code.
You are. And the cognitive load of doing that is just immense. The developer has built an environment that is actively fighting against them.
Yeah.
They are spending their mental energy plugging structural holes that just shouldn't even exist in the first place.
And that has to affect the end product.
Oh, it bloats the application, it makes the code base incredibly difficult for new engineers to read, and it practically guarantees that a bug will slip through eventually.
Right.
Because human beings are notoriously bad at anticipating every single contradictory state an asynchronous system might encounter.
So we have the messy, defensive, frankly exhausting reality. We're trying to build perfectly disciplined humans instead of perfectly designed systems.
Yes.
And this is where Aang pivots to the elegant solution. We stop playing the defensive game and we fundamentally change the rules of the environment.
Exactly.
And Aang does this by turning to Haskell. Now, I know Haskell is known for having a notoriously strict static type system, but I've built applications in JavaScript and Python. I could just write a quick validator function to check my state. So why do we need a strict compiled language like Haskell to solve a problem like UI state?
That is the crucial distinction right there. A validator function in JavaScript or Python is a runtime check.
Meaning it happens while the app is running?
Exactly. It means the application has already been booted up, the code is actively executing, and your validator's running around frantically checking if anyone flipped the wrong switches.
Okay, I see.
It's like having a security guard checking IDs inside the club after everyone is already mingling.
Right, someone could already be causing trouble.
Exactly. Haskell's static type system, on the other hand, operates at compile time. It's the architect designing the club without doors so unauthorized states physically cannot enter the building in the first place.
So it happens before the app even runs.
Long before. The compiler in a language like Haskell acts as an unpassable bouncer. It analyzes the fundamental grammar of your logic before it ever converts your text into executable software. So Aang's approach is, don't write a rule that says, please don't flip all three switches at once. Leverage the static type system to make it syntactically impossible to even write the code that represents that invalid condition.
Think about the gravity of that phrase for a second. Syntactically impossible.
It's huge.
If you try to write the logic for state 5 where it's loading, failing, and succeeding all at once, the computer won't just crash when a user clicks a button. The compiler will refuse to even acknowledge your code as valid software.
Yes, it's like trying to write a grammatically correct sentence in English using only integers.
Right.
The structure of the language rejects it before it even leaves your mouth. This completely shifts the burden of correctness from the developer's memory to the compiler's rigorous mathematical checks.
The system takes on the cognitive load for you.
Exactly.
So I want to translate how Aang actually achieves this in the Haskell code without, getting bogged down in reading raw syntax aloud. Because what Aang does is conceptually beautiful.
It really is.
Aang completely throws away the 3 independent switches. They just rip out iLoading, has-error, and user data. They are gone.
And in their place, Aang defines a single unified concept, an algebraic data type. Let's just call it the UI state.
Right, the UI state. And Aang gives this single UI state 3 strict, mutually exclusive flavors.
Let's hear them.
Flavor 1 is loading. And Aang notes this only means loading.
Yep.
Flavor 2 is error, which holds an error message. This only means an error happened.
Correct.
Flavor 3 is success, which holds the payload. This only means we have data.
The secret sauce there is that mutual exclusivity. It is a single slot in memory, and you can only put one peg into it at any given time.
Right.
It is structurally impossible for the UI state to be loading and error simultaneously because they are just different variations of the exact same entity. You can be one or you can be the other. You cannot be both.
So going back to our control room analogy, the 3 independent wall switches have been ripped out. The wires have been completely pulled from the wall.
Goodbye to those.
And they've been replaced by a single physical rotary dial on the desk.
Yes.
The dial can point to loading, it can point to error, or it can point to success. You physically cannot turn a single dial to point to 3 different things at once.
The geometry of the interface prevents the contradiction. And look at what happens to the math when you do that.
Oh, right.
We don't have 8 possible states anymore. We don't have 2 times 2 times 2. We have exactly 3 distinct states.
Because it's just the 3 positions on the dial.
Exactly.
So the 5 illegal states, including our absolute nightmare state 5, literally no longer exist.
Poof. Gone.
They are, as the title of Eng's post promises, unrepresentable.
They are mathematically banished from the universe of this application. You are no longer defending against bugs. You have designed an architecture where those specific bugs simply do not have the oxygen to survive. You have completely removed the environmental conditions that allowed them to exist in the first place. The race conditions, the UI tearing itself apart, the infinite retry loops caused by conflicting state flags, all of it is wiped out by a single structural change.
That is just incredible. But preventing those nasty runtime errors is almost just the baseline expectation here.
Right, there's more.
Eng highlights an incredible secondary benefit to this approach, a benefit that impacts the actual human beings who have to read, maintain, and live inside this codebase months or even years down the line.
Yeah, this is where we talk about the graveyard of legacy code.
No,
Because if those 5 illegal states are structurally gone, then all the baggage that came with them disappears too.
the hackish logic,
Yeah.
all those exhausting lines of defensive code, the massive nested if statements, checking if loading, make sure error is false.
All of it vanishes. You just don't need to write code to handle impossible edge cases because, well, the edge cases are no longer possible.
The compiler guarantees it.
Exactly. You have completely decluttered your application. You've removed all that scaffolding, and you're left with just the pure intentional business logic. And Eng notes that this creates a system that is fundamentally self-evident.
Code as documentation. I absolutely love this concept.
It's the holy grail.
Because usually documentation is this separate, rapidly decaying text file that no one actually reads and no one ever updates.
Right.
But Eng says the data type definition here immediately tells us exactly how the system works, simply by reading the structure itself.
Think about a new developer being onboarded to this project, say, 6 months from now. When they look at that single rotary dial, the UI state, with its 3 clear flavors, they understand the entire flow of the API call instantly.
Without having to guess.
Exactly. They don't have to dig through hundreds of lines of hackish, defensive if statements to reverse engineer what the original programmer was trying to prevent.
Or what mood they were in that day.
Right. They don't have to live in fear of deleting a seemingly useless piece of code because they aren't sure what obscure edge case it was defending against. The structural boundaries of the system are clearly explicitly drawn by the types.
The architecture just speaks for itself. So what does this all mean for Eng's work? I mean, where is this philosophy going next?
Well, Eng actually signs off the post by mentioning that this isn't just a theoretical academic musing.
Oh, nice.
In upcoming posts, Eng plans to apply this very concept to a pet Haskell project, working through numerous refactorings.
So taking it into the real world.
Right. Eng is embarking on a project of comprehensive environmental redesign.
Okay.
This isn't just about going into a pet project and squashing a few bugs with a debugger. It's about tearing down the underlying infrastructure that allowed the bugs to spawn in the first place.
Right.
And replacing it with an architecture built on mutual exclusivity and absolute clarity. It's a fundamental shift from bug fixing to bug prevention through design.
It's an incredibly powerful way to look at problem solving.
Yep.
So to sort of wrap up our deep dive today, we started by looking at a common structural trap.
Yep.
How relying on independent variables, those separate light switches, creates a massive mathematical expansion of hidden illegal states.
The 8 states.
Right. And we saw how this forces developers into a deeply defensive posture, constantly writing exhausting, hacky code to catch inevitable contradictions.
Constantly fighting the system.
Exactly. And then, through Eng's insights on Haskell, we explored the paradigm shift. By enforcing mutually exclusive states through a static type system, allowing the compiler to basically act as our bouncer, we make those illegal states syntactically unrepresentable.
Which is just a brilliant phrase.
It really is.
Yeah.
The result is software that is not only robust and bug-resistant by design, but fundamentally cleaner and entirely self-documenting.
Which leaves us with a truly vital question to reflect on for you listeners.
Okay, let's hear it.
Eng's post is strictly about software architecture, right? About eliminating defensive programming by making bad states unrepresentable in a compiler. But step away from the keyboard for a minute and think about your own daily life.
Okay.
Think about your teams, your organization, or just your daily workflows. How often are you absolutely exhausted from practicing defensive logic in the real world?
Oh, man. Like writing those convoluted multi-paragraph emails just to prevent a potential misunderstanding.
Exactly. Or constantly double-checking someone else's work, or juggling complex project management tools where the status tags constantly contradict each other.
Yeah, or a task is marked done, but also needs review.
Right. You are managing flawed systems, you are dealing with human workflows that have allowed illegal states to exist.
Wow.
So what if, instead of constantly trying to catch those inevitable human mistakes after they happen, you took Ng's approach? What if you stepped back and simply redesigned the type system of your workflows, the fundamental rules of engagement, so that those collisions, misunderstandings, and mistakes became structurally impossible to make in the first place?
So where can you install a single rotary dial instead of relying on 3 independent switches?
Exactly.
It's a question that might just change how you design everything around you. Well, that's all for today's deep dive into Ng's notes on Haskell. Keep questioning the structure of things and keep digging deep into the material. We'll catch you next time.